Hello, my name is Matthew.
I'm Sarah.
I'm Lisa.
I'm Ben.
And I'm Akshay.
And we're here to outline our design and manufacturing process, as well as the execution of our culminating project, where we were tasked with programming an industrial robot for brush painting. This presentation will discuss the following subjects. First, I will introduce the problem, task, and purpose of this project, and I'll also show our brush fixture that we made in response to the task, and the drawing it made while equipped on the ABB robot at the Dow laboratory. Lastly, I will describe the results we achieved with our fixture and how we navigated our deadlines throughout the project. Next, Ben and Akshay will go into more detail about our design and manufacturing processes, including the CAD modeling and additive manufacturing required to produce this fixture. They'll also expand upon potential future improvements with their projects. Lastly, Lisa and Sarah will close out this presentation examining the social science behind robotic art, detailing its impact and a study plan to quantitatively analyze the impact. They will also close out with some concluding remarks and detail a couple key takeaways from this project. There are many different forms of art that currently exist, including drawing, sculptures, and paintings. However, the problem with this handmade art is that it is expensive for consumers, mainly because they are unique and require a lot of time and effort to make. They also cannot be mass-produced because a person is not capable of creating identical pieces at a high rate while maintaining quality craftsmanship. Lastly, another problem with traditional handmade art is that some people have creative ideas, but are actually not skilled enough to produce their concept in their head. Robotic art could change that. Our overall term project task was to create an original pen holder that is compatible with an ABB robot. To do this, we fabricated our pen holder using computer-aided engineering and additive manufacturing techniques. That is, we designed a CAD model of our design and printed it out using a 3D printer. Then we programmed a toolpath containing the coordinates of our drawing using RobotStudio, and finally equipped and executed the program on the ABB IRB 140 robot. This presentation will outline these processes over the course of our term project, as well as the societal significance of robotic art, particularly in regards to the expansion and accessibility of art with the help of industrial robots. In response to this task, we produced the pen holder, pictured on the left when it was attached to the pen and robot's flange. It is characterized by a serpentine string to absorb stress and an upright vertical design. The picture on the right shows the complete installation of the fixture on the ABB robot. We used set screws and holes to secure the pen to the fixture, and then the fixture to the robot's flange, which allowed it to be attached to the ABB robot. Once installed, the robot is enabled to draw a design according to a pre-programmed toolpath, containing the coordinates for the robot to reference in the drawing. We will now play a short video showing the robot draw the penrose triangle, an elaborate optical illusion with the help of our paintbrush holder. So here's a better view of our final design on the right. Compared to the intended toolpath that we simulated in RobotStudio on the left beforehand, it is safe to conclude that we successfully drew the penrose triangle using the ABB robot. In regards to executing this vision, we developed a tangible schedule for the important milestones as illustrated in the Gantt chart above, which we closely followed throughout the project. In general, each of our projects followed a parallel structure where we spent the first part on discussing ideas, then putting them into action, and finally reflecting on our work in our reports. We only had to change our schedule only once due to deadline extensions. Consequently, it is apparent that we spent a disproportionate amount of time on the final presentation and report, shown in light blue in the bottom right. This is because we didn't stray from our schedule, so we ended up with much more time than intended for this portion of the project. Next, Ben and Akshay will discuss the design and manufacturing process.
Thanks, Matt. So when brainstorming our design, we used a combination of both CAD and physical drawings. Our CAD software of choice was Siemens NX. However, any CAD software would have worked. Our initial version took a lot of inspiration from the professor's original model and admittedly was very similar. So in order to create a more original team project, we decided to scrap that model and begin on version 2. Version 2 started off with a physical sketch submitted by each of the team members. We eventually chose Akshay's because we believed it gave us the best overall design as well as functionality. However, when implementing this design in CAD, we noticed some problems meshing the two halves of the parts together, as well as we forgot to add a part for the flange and pen to be attached without them hitting. So unfortunately, due to these constraints, we had to scrap the model. And then move to our final design. So when we looked at our final design, we asked ourselves, what did we like? What didn't we like? What worked and what didn't work? Something we kept pretty consistent throughout the whole process was the spring functionality. So going off this design, we improved the process just a little bit by making it about an extra millimeter thicker, just to improve structural stability overall, as well as make it a little bit less prone to breaking if we were to accidentally run the robot into the build plate, as we are still new to industrial robots. In order to hold the pen, we decided not to offset it at an angle and make it more vertical and in line with the flange, because the pen we are using, which is a pen brush, has a softer tip compared to Sharpies and markers per se. So we would not have to apply as much vertical pressure to the build plate and hence less bend in our part. Worst comes to worst, we did believe that if we needed to offset our pen at an angle, it would be easier just to angle the robot. Combining these two parts together, we got our final design. Taking a little bit step back, we started our CAD, some techniques we used in CAD. We started with a two-dimensional sketch of what we wanted. We then used the extrude tool to essentially pull out the part from the page, creating a 3D model of what we wanted. Using the extrude tool again, with the subtract feature, we were able to create holes for the pen, flange, and set screw. Finally, we were able to use the edge blend tool to get rid of any sharp corners or edges and just to essentially round out our part and save a little bit material while we're at it. I'm going to now pass it off to Akshay. He's going to talk a little bit more about when we exported our file and how we 3D printed it overall.
Thank you, Ben. So we first converted the CAD model into G-code instructions using Cura, and our specifications was the layer height was 0.2 millimeters at 75 millimeters per second. And then we added a brim and support structures for more stability during the printing process. And then as shown on the right, the infill at thin edges, we did 100%. And at the thicker top part, we chose 20% because there doesn't need to be much inside of that area. Okay, so for 3D printing, we followed the initial safety precautions and then used the USB drive to upload the G-code program to the 3D printer. And then there was leveling and temperature calibrations to make sure that the bed plate was at the right level and that the plastic isn't too hard or too soft for the temperature. And then the 2.5-hour printing process began, and we observed the printing of the first few layers to make sure that some of the common failures don't happen early on. And after the print, we let the part cool and then removed it using a spatula. And then after printing, we used pliers and a screwdriver to remove support structures. We also discovered that the pen hole was too small for the pen. So even after sanding the inside of the hole, it was still too small. So we came back to the fabrication studio a week after to print a modified version of the pen holder. And now we'll talk about the execution of project and future improvements. So for the setup and execution of the Penrose drawing using the ABB robot, we started off by inserting the flanges rod into the central hole of the fixture and securing it with screws to secure it to the pen holder. Then we defined the work object by defining a work object variable for our fixture called toolpen2. So now the robot has a reference frame for calibration. And to actually calibrate it, we have to take 3 different calibration points around a predetermined point, and that point was the tip of the rod. And then we jog the robot so that the brush pen tip barely touches the whiteboard to run the code. And then finally we run and execute the code. Now I'd like to pass it on to Lisa to talk about problems and solutions.
Thanks, Akshay. So first, we'll talk a bit more about problems and solutions, particularly some of the problems that we faced post-printing of the pen holder. So one of the problems that we faced throughout the process was the fact that some of the internal support structures were inaccessible, particularly some of the support structures inside the spring of the pen holder. Some of the ones that were a little more accessible than the others, although still not perfectly, we were able to remove with curved pliers, but some were so difficult to access that we ended up having to actually punch them out with a screwdriver. Another problem that we faced was that the set screw holes were actually too small. And so in order to widen them, we used hand drills. We also faced some problems during the in-person lab. One of the issues that we witnessed was that some of the lines on the drawing had an uneven thickness due to the unlevel bed. And so in order to fix that, we coded the robot to trace over the lines twice. And that ended up allowing the drawing to look a little more even. We also admittedly experienced some human error during the calibration of the reference frame. And in order to solve that, we ended up needing to recalibrate the robot during that running of the lab and the robot to make it more accurate. So some future design improvements, mostly we were satisfied with our design, but we did think there were a few things that could be changed. First off, we could certainly make the whole dimensions more accurate right from the beginning so that we don't have to make all kinds of physical modifications. And it would potentially also help to actually offset the pen to an angle. For the purposes of our design, it did help a bit to have our single dimension straight line pen holder in terms of calibration, but that actually made the act of drawing more difficult. And we thought that adding back in an angled hold could potentially help that. The drawing, we also thought might need to be modified or selecting a new one altogether, one that doesn't retrace lines, simply because this turned out all right since we were drawing on glass, but on any real piece of paper, the act of retracing constantly the way we did would have caused the ink to bleed through. So now I'm going to pass it off to Sarah, who will talk some about the social science impacts and our social science study plan.
Thank you, Lisa. So robotic art has social impacts that affect both the artist and consumers in various ways. In regards to the artist, robotic art can help people who could not create traditional handmade art due to physical disabilities or other extenuating circumstances to produce their own works. Robotic art can also enable artists to sell to a larger market. And then regarding the consumers, robotic art benefits them by decreasing the cost as a result of the ability to mass produce works and to increase the accessibility and availability of each work. Additionally, it reduced the stigma that art is not a reliable career, as each work of art could be mass produced for a larger consumer market, and new works can be produced at a faster, more frequent rate with the same level of quality. Our study would examine whether people can differentiate between robotic art and traditional human-made art, and how their willingness and how their awareness of the method used to create the art would affect their willingness to purchase it. We would ask individuals receiving income to determine how multiple pieces of art were created and to rate their willingness to buy each piece on a scale from 1 to 5 via a survey. Afterwards, the true method of creation for each work would be revealed, and the participants of the survey would be asked to rate how likely they would be to purchase each work based on the new information. This study would help us determine how the mode of creation would affect consumers' inclination to purchase works of art. We would ask participants to also include their age, income bracket, and education level at the beginning of the survey to help us determine if patterns can be found based on demographics when analyzing the results. Finally, we would also consider asking participants to rank a small list of factors in the order of what they value most to what they value least about art. This list could include price, creation method, and how many copies are available. This would help us draw conclusions about how willing people would be to purchase robotic art. The research question that our study would try to answer is, can people tell the difference between robotic art and human-made art? And how does the method of creation affect their willingness to purchase it? We predict for the results that people will not be able to differentiate between the two, but that their willingness to purchase the works of art might change once they discover how it was created based on what they value most about the art. If the consumer is currently able to afford the work of art and they value the time, effort, and uniqueness of the work, they will not likely buy robotic art. If the consumer is currently able to afford the art, but they value the cost more than the uniqueness of the work, they might consider buying robotic art because it would be less expensive. And if the consumer is not currently able to buy the work of art, then they will likely want to purchase robotic art because it is now more affordable. So now I'm going to pass this back to Lisa, who will conclude our presentation by giving an overview of our closing remarks and key takeaways from our project.
Thanks, Sarah. So in conclusion, we successfully designed and manufactured a holder for the pen that is compatible with the ABB IRB 140 robot with the flexibility and strength needed to oppose the drag force of the pen. Though some changes could be made, the design was, on the whole, successful. We also programmed the ABB robot to run an assigned toolpath and completed an in-person simulation of the robot toolpath. Our work serves as a foundation for mass production of parts in art industry, mass production of art, and increased accessibility for artists and consumers. So some key takeaways. We learned a lot over the course of this semester. We gained an understanding of the computer-aided design process and manufacturing, learning how to use CAD, particularly the sketching and assembly functions, Kira, and 3D printers. We explored the process of using the RobotStudio program to program a toolpath for the robot to follow. We learned how to actually interact with industrial robots, including how to use a pendant and how to calibrate a reference frame. And we were also exposed to the ways in which robots can have problems and make mistakes, even when you do your best to make sure all of your work is correct. Finally, we developed some understanding of how robots and manufacturing can impact our society, even in seemingly unrelated areas like art. Thank you for listening to our presentation. We hope that we've presented you with a solid outline of our project over the course of this semester.